To most of us, photography has been the means of capturing some of the memorable occasions we've known. Pleasant reminders in the days to come. Snapshots of loved ones, of dear friends, a cute baby, or that pretty girl at the beach. This is the popular understanding of photography, and rightly so, for the action or results are matters of personal concern. There is, however, another field of photography, not so well known, but of much more importance, and that is the use of photography in its varied application to science. In the photography of science, there is no conjecture. Thousands of scientific eyes in thousands of scientific cameras say this is what happened. Here is the record and the information for further progress. But let's first consider what photography is and how it works. Basically, it is a graphic record of light or radiant energy. That means light can fall directly on a photosensitive surface, or if it passes through a lens, an invisible latent image of the light source is formed. Chemical development makes this a visible and permanent image. This is familiarly known as the negative. From the negative, prints or positives may be made in any quantity. These are called still pictures. When you see a movie, you are looking at a series of still pictures photographed in rapid succession. Project the pictures at the same rapid speed, and you've got motion pictures. That's the simple mechanics of photography. Now let's consider some of its uses. The Navy desired certain dental information, so it built this unique camera to do the job. By using an angled mirror in the mouth, the camera takes pictures of tooth decay, which in itself is not important, but if the same dental weaknesses are found in 1,000 Navy men doing the same duties, it has a significance worth checking and correcting. Special cameras are devised by the Navy for special jobs. In the testing of aircraft, the pilot may wear a camera strapped to his chest to record his instruments. When the Navy tests a plane, as in the case of this helicopter called the Flying Banana, it wants an accurate record of every phase of the test. That means it wants a photographic record that can be studied for corrective values. And one that proves beyond any question the performance qualities of the plane under test. Just such an application of photography, wherein it furthers the development of a scientific mechanism, is to be seen in these guided missiles suspended from the wings of the mother plane. Navy pilots follow and picture the drop-away and flight until the missiles find their intended target. The accuracy of the mechanism is due in no small part to the photographic check of every step in its development. Airplanes are not built with cameras, but they certainly are a factor in predetermining design, construction, and maneuverable efficiency. Smoke introduced into the airflow shows photographically how the scale model will react at given speeds. Here's a unique application of photography. The Navy utilized this human centrifuge to find out how much gravitational strain a pilot could stand in pulling up from a dive. The camera disclosed the additional information that it was the blood draining from the head that caused the pilot to black out. So the Navy devised a special flying suit that gave strength and support to the blood vessels and enabled their pilots to fight off the crippling faintness. Much of the Navy's photographic research and findings are passed on to civilian use, and that is particularly true of this model basin. Designed to test the hull models of every ship intended for Navy service, the basin extends its facilities to every sizable American ship being built today. In this laboratory, conforming to the exact curvature of the Earth, the camera aids science in determining the sailing characteristics of the ship before it is built. Such foreknowledge is absolutely essential in shipbuilding today. Rocket research makes extensive use of photography. The rockets are followed in their flight, and every detail of their performance is recorded on film by Cinetheodolites for measurement and study. In other tests, rockets are fired so that they will travel along a fixed guide rail. This permits an even more accurate method of timing and analyzing the experiment. Many cameras record the test from many positions, each chosen to reveal a clear film report of the rocket's characteristics. Let's consider the role of photography in experimental science. A series of ultrasonic frequencies that are beyond the range of hearing cause these interesting designs called Chladni patterns. How's it done? Well, there are crystals under the plate. They vibrate at high frequencies and cause the sand to move to the places of least vibration on the plate. What is science trying to prove? It isn't so much the proving as the improving. By being able to study the constant vibration characteristics of the crystals, scientists can improve sound communications, such as in your telephone or in underwater sound detection apparatus. Underwater sound detection is important, especially if you're in a submarine. That's why they use this oscilloscope to detect and picture the sounds. Here you are literally seeing speech. In the study of underwater sound, these patterns are photographed. This is the sound made by porpoises. Snapping shrimp. And a submarine being depth charged. This brings up another phase of photographic technique. If a metallurgist wants to analyze this flow of molten steel, he has to slow it down. That's done by using a high-speed camera and taking 1,000 pictures a second. In such fashion may be studied the flow characteristics that could not be obtained otherwise. The Navy is interested in observing the flight of a bullet. This camera, called an optical chronograph, catches it in midair and discloses the sound and shock waves in its trail. Those sound and shock waves play their part in determining the penetration power of a bullet. Here is what looks like a graph, but is an actual photograph of a projectile entering armor plate. The slope of the curve shows the rate of slowdown as it enters. Now, the Navy didn't build this hammer just to smash the radio. They want to find out why the radio shatters when the big guns sound off. So they rigged the hammer to simulate the shock of gunfire. To really see what happens, let's study the results in slow motion. That base block of the radio is weaving and bending. Make it heavier and stronger. The tubes are located improperly. Redesign will help. In such fashion, the corrections are noted and made. Just one more instance of slow-motion photography, and it is interesting because the results were slightly opposed to popular belief. The Navy filmed the effect of underwater explosions, and at 2,000 frames a second, discovered that the explosive force after exploding started to bounce with the pressure of the water compressing it against itself. A second explosion shows the explosive force moving toward a fixed objective. Here was a clue to new shipbuilding possibilities. The conception of underwater explosions may well have to be revised in view of this slow-motion photography. This crystal, shown in time-lapse photography, took 2 days to grow. We see it happen in a few seconds. Instead of shooting 1,000 frames a second, one frame was shot every 1,000 seconds, or one every 16 minutes. By the use of this camera technique, the Navy scientist is enabled to observe the growth of matter, in this instance crystals, and check on the good or bad characteristics. Supplementary light sources provide interesting technical uses of photography. You can't see ultraviolet light, but when you apply it to these luminescent materials, they transform the ultraviolet into visible light. This is known as fluorescence. Some of these materials store energy from the ultraviolet and glow for some time. This is phosphorescence. For its own purposes, the Navy classifies these respective luminescent materials and their degrees of phosphorescence. Photography indicates whether the material can be used for a television screen, radar screen, or whatever the application. The significance of photography in medical research is long known. It has been an active associate in the study of disease, and no small part of our combat strength in that field is due to it, such as this Navy experiment to determine the rate of flow of the brain's circulatory system. An injection of fluorescent solution into the blood and the use of ultraviolet light gives a glowing image that establishes the rate of flow. Much of the information gained by the Navy in its experimental photography is passed on to others. This X-ray camera, or radiograph, detects the flaws in construction material. The research value of these experiments is available to the testing laboratories of industry. That same technique of X-ray and motion pictures can be of considerable importance in medical research. It permits a visual analysis that removes any question of doubt. Theoretical diagnosis is replaced by photographic proof. Let's suppose that test engineers want to determine how a machine part will stand up on the job. By taking a plastic model of the part, subjecting it to a direct pull of proportionate pounds, and then passing polarized light through the model, they obtain a picture of the points of stress. The square part shows 4 points of stress. This round part, however, shows only 2 points of stress. Therefore, the round part is stronger and better designed to do the job. These ladder-like patterns are supersonic shock waves, and their photographic reproduction by means of the Schlieren system has been an important contribution to the advancement of jet propulsion and rocket design. Let's say the Navy wants to check the efficiency of a ship propeller and observe its action at various pressures. A stroboscopic light flashing on and off at the same speed as the propeller makes the propeller appear to stand still. Study of the bubble wash will check the propeller's efficiency. Photography, as you may have assumed by now, has many and varied scientific uses. This electron diffraction camera is a case in point. Photographed in a vacuum chamber, these concentric rings are the film pattern of a tiny crystal. The crystal diffracts a beam of electrons, and we get this pattern from which the crystal structure can be studied. The value of photography, of course, is not only that it records instantly what we wish to see, but that it also records it permanently. Astronomy has made excellent use of these factors. 90% of the instrumental work in today's observatories is being done by photography. and that is because a constant and accurate check must be kept of the solar system. Accordingly, many of the Navy's observatory telescopes are equipped to photographically determine the movements of the outer universe. There's an exactitude about this spiral cluster that indicates advantages of the photograph over visual observation. It is not suggested, of course, that photography will replace the skill of the astronomers, but rather that it supplements their work and lends verification to their findings. This telescope has a 40-inch lens and yields some interesting pictures of the moon, which in themselves, of course, are not unusual, but just such photographs have substantially aided in measuring its surface, the altitude of its craters, and their structure. With the new and far more powerful telescopes being readied for science, photography will unquestionably aid in revealing new secrets of the planetary system and of this crater. And as in this actual picture of the moon in motion, we will be able to bring the as yet unknown within photographic observation. Science is constantly seeking additional information on the growth and structure of matter. That requires special cameras for special purposes. This one photographs the crystalline structure of metals under a low magnification, and in the language of the laboratory, this is called macro photography. Science designed this camera for much greater magnification and uses it for microphotography. As the name indicates, it makes possible a microscopic study in film of metallic structure. Any test sample can be pictured and studied for flaws. And that is the important thing in all these photographic observations, whatever the scientific application of the camera. The subject for observation can be studied and studied, and in as many varied ways and lights as will accurately determine the information sought. To us, these may seem pretty pictures, but to the scientist, they are the medium of observation that gave him the contour, the surface structure, and the internal stress patterns of a crystal. By studying the photographic results, Navy scientists learn a little more about how crystals are made and grown. These peculiar goings-on are 100-time magnification of a parasite in the blood of man. They are known as Schistosoma mansoni, which doesn't soften the blow if they attack. They cause a dreaded disease known as snail fever. The Navy has a particular interest in stamping them out. We step up the scale of photographic magnification to the electron microscope. The electron microscope substitutes magnetic fields for glass lenses and an electron beam in a vacuum for light. This makes possible the magnification at 1,000 diameters of this metal organic crystal. It enables us to picture a diatom, which is a microscopic single-cell living organism and is magnified here to 6,000 diameters. Such tremendous magnification, as of these crystals, represents one of the many steps forward facilitated by photography. A great forward step was the development of this X-ray diffraction camera used in atomic research. We told you that diffraction meant the breaking up of a beam of light. In this instance, a crystal of iron diffracts the X-ray beam. From the intensities and angles of this diffraction, science has been able to approximate the atomic structure of iron. The photographic image appears as a series of spots which are measured, patterned, and superimposed on a single plate. This resulting image, magnified 500 million times, is atomic structure. The story cannot yet be told, but you can be certain that photography played its part in this. The advancing strides of photography fortunately contain their own proof, else one might doubt what is about to be shown. A Geiger counter telescope detects the path of the cosmic rays and causes them to electronically light certain patterns of neon tubes. Cosmic rays cannot be seen, but through photography, a fair approximation of their activities, such as direction, rate of arrival, and energy, can be recorded on film. There is additional evidence on the workings of cosmic rays to be found in this cloud chamber, an apparatus designed for photography in the stratosphere. By the use of a sealed water vapor chamber, the passage of cosmic rays is pictured first as a single trace. Then in the form of a double trace, from both of which can be determined their direction and energy. Lastly, as a shower, in which science finds a direct relationship between cosmic rays and nuclear reactions. Here is the most interesting timepiece in the Western Hemisphere, for the singular reason that it keeps the correct time for the Western Hemisphere. It is located at the Naval Observatory and is set by the photographic observations derived from this camera. In the bright lexicon of observatory language, there is no such word as about. The time here is calculated within 1/2000th of a second. At stated intervals, the Navy sends the correct time to all channels of communications. Here is the pleasant and gracious keeper of one of the largest cameras in captivity. It is the Navy photoheliograph and takes pictures of the sun and of sunspots. Every time our radio communications are disrupted, we blame it on sunspots. Well, here they are, and so gigantic in size that the Earth could be dropped into the smallest of them with scarcely a ripple. By keeping photographic check on their appearance, the Navy enables military and civilian agencies to reroute communications. Now we are getting into the realm of what used to be Buck Rogers' exclusive territory. This V-2 rocket spectrograph takes films in the ionosphere, 100 miles above the Earth. The camera is, of course, automatic, and the exposed film feeds into this steel chamber, which is recovered when the rocket falls to Earth. This spectrogram, taken in the ionosphere, is a notable achievement, for it forms the basis for study of a region impossible to photograph from the Earth. Densities in the spectrogram can be measured to determine the intensity of the sun's radiation in the ionosphere, and that is important to research. Scientists want to know what is out there before man tackles it, as man assuredly will. The Navy is now engaged in exploring those outer spaces. Their scientists and those of many research agencies are seeking the answer to what has long been speculation and theory. Their laboratory is aloft in the nose of a V-2 rocket, 100 and more miles above the Earth. The instruments of science have replaced the instruments of destruction. Men of research have replaced men of destruction. The sword of uselessness has been turned to the plowshare of knowledge. We are in the dawn of scientific potentials that may well bring to mankind an era of accomplishment far beyond all current knowledge. These captured films are evidence of the importance Germany attached to photography. Many of the V-2s were faultily constructed. The Germans had to find the mistakes and correct them. Study of the film reports in these instances was discouraging. This American rocket, on its flight to outer space, is perhaps illustrative of our photographic efforts. We have come far, but it is only a beginning. The horizons ahead are unlimited. The greatest photograph ever taken, this actual picturization of the Earth's surface from a height of more than 100 miles is a symbol of the ever-broadening field of research, testing, and development to which photography is advancing.